Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be predicting the formation of ions and molecules using ionisation energy. Okay, so in the previous kind of videos we've been developing this concept of what we mean by ionisation energy. And thinking about it, and we've defined it as it's the energy that's required to remove an electron from an atom. So the energy required to turn it into a positive ion by removing one electron at a time. We've had a look at some of the trends in ionisation energy and then atomic radius as we progress through the periodic table, going across a row and then down a group, and to help us to develop some patterns about how an atom is actually structured and developing evidence, experimental evidence, that supports the idea of electron shells with a fixed capacity. Okay, that along the lines of what the Bohr model suggests or kind of includes. But one thing that we can also use ionisation energy for is to be able to predict what will happen to an atom, whether it will form an ion or whether it will form a molecule. Okay, because a while ago now, we introduced the idea that some compounds form from ions and some compounds are molecular, or form from molecules, which are neutral and have atoms connected or bonded together. And so what we're looking at now is, okay, well, we identified that we could do this, or that an atom would do this, and we looked at some patterns in how they would do that, but not with an explanation of why they would do it, or being able to actually come up with more definite kind of model for how this happens. And so in this video, we're going to look at using ionisation energy to be able to predict this. Okay, so using because we've seen that it's related to how easily electrons are taken away from an atom, and so it's also, we can look at it as a measure of, we can use it to measure the attraction of electrons to the nucleus of its atom. So what we're going to do now is we're going to set up some arbitrary rules that we're going to use when we're looking at the first ionisation energy of an atom, so the energy required to remove the first electron, and use that to then sum up the attraction as either strong, intermediate, or weak. Okay. So what we set up here is a spectrum of the values for the first ionisation energy. And I've set up two particular numbers here which are relevant. Okay, at the moment I'm just setting up these rules so that you know how to use them, not really explaining why it's these numbers at this stage. But so what we can say is, all right, if an atom has a first ionisation energy of less than 7.8, then we're saying that its electrons are very easy to remove. Okay, so we would say that it's a weak attraction if it's less than 7.8. Okay. If we look at the other end of the spectrum, if we see a first ionisation energy of greater than 10, then we would say that that is a strong attraction. Okay, so that might be 25 or it might be 12. Okay, but if it's above 10, that we would consider that to be a strong attraction of those electrons to that atom. And so then in the middle, we would say, okay, well, if it's not weak and it's not strong, then it's somewhere in between. So we would define that as an intermediate. Okay, in between these kind of markers of 7.8 and 10. And now we're going to look at the elements that are in these three categories. They tend to do different things in terms of forming ions and molecules. And so we're going to kind of articulate that so that we can start to see that if an element falls into one of these categories, we can expect what it's going to do. So if it's got strong attraction, that element will tend to form negative ions. Okay, now not exclusively, like what we're going to see in these is that they're more like guidelines than concrete, unbreakable rules. But we're seeing that they tend to form negative ions. Likewise, if an element's got weak attraction for its electrons, it's less likely to actually hold on to its own. So it's more likely to form positive ions. Okay, so negative ions for something that's strong, positive ions for something that is weak, and in the middle, if it's intermediate, that it generally don't form ions. Okay, so this is where we're thinking about molecules tending to be formed. Okay, so that if we can identify which category that these elements fall into, we can predict whether it's going to either gain electrons to become negative ions, lose electrons to become a positive ion, or tend to stick to other atoms to form a molecule instead. Okay, so when we look at that first ionization energy, we can decide which category, we can then make those predictions. And what we can do now is we can also go just that little bit further to be able to predict, all right, well, if we're going to lose or gain electrons to form ions, how many are we likely to lose? Okay, so if an element is likely to lose electrons, it will lose all of its valence electrons, or its kind of outer shell final electrons. Okay, so that should say will lose all of its valence electrons. So if it's got 2 valence electrons, you lose 2. If it's got 1, it will lose 1. If it's got 3, it will lose 3. If it's got 4, it will potentially lose 4. But what we can see is that you do tend to have a limit of less than 3 or fewer electrons. Is really the practical limit. 4 can be lost from some, but things that would tend to have 4 valence electrons you'll find will tend to be in this middle category. Okay, now if we're trying to gain electrons, then we can identify, well, how many electrons would we need to gain? Is there a target? Is there or a level, a maximum level that we would reach? And so we'll gain as many as needed to fill valence shell. Okay, and so that would be either 2 or 8 electrons, depending on where we're talking about here. So it would be 2 if we're thinking about something that's really small, so thinking only about filling up that first shell, so hydrogen. And then if yeah, so gaining to go up to that, or to gain up to 8 valence electrons for just about everything else. Okay, so that's kind of fleshes out those rules a little bit further for you, so that you can now use those, and the rest is over to you. All right, thanks very much for watching. Bye for now.